Jai Hind everyone, myself Dr. Vanna Sharma from Ajay Kumar Garg Engineering College. My subject is Engineering Physics, code is KS101T. The topic which I have started, that is wave optics, and under this wave optics we have discussed about the different phenomena involved in interference, and after that we have discussed about diffraction. So in case of interference, we have discussed about what are coherent sources, how the coherent sources are generated, two different methods for generating coherent sources like division of wavefront, division of amplitude, and specifically in our syllabus we are having division of amplitude. We are having examples of division of amplitude like interference in thin films of uniform thickness, non-uniform thickness. So as you have seen some beautiful colors on a soap bubble in the presence of sunlight, that is an example of interference in thin films. So we have discussed about the interference in thin films of uniform as well as non-uniform thickness, that what are the conditions under which you can get those beautiful colors in a thin film of uniform thickness or non-uniform thickness. Then we have discussed about a famous experiment which is our Newton's ring experiment, and we have discussed there that how the interference pattern is obtained in the form of that concentric circles and rings there. And after that we have calculated the diameter of different rings like bright and dark rings, and using that experiment we have found that we can calculate the wavelength of any unknown source of light. We can calculate the refractive index of an unknown liquid with the help of that experiment. So that is a very famous experiment and important experiment in interference. After that we have started our diffraction part, that second topic of wave optics. And in wave diffraction, we have discussed about single slit, double slit diffraction and N slit diffraction. So today I am going to take the last topic of diffraction, which is mentioned in our syllabus. So let's start for today's lecture then. These are the reference books which you can take for this topic of diffraction. A textbook of optics by Ajoy Ghatak, Brijlal and Subramaniam, a textbook of engineering physics by Navneet Gupta, and engineering physics by S.K. Gupta and S.L. Gupta. So the various topics which we have already covered, we have covered the introduction of diffraction, then types of diffraction, that is Fresnel and Fraunhofer diffraction. Then we have discussed about the single slit diffraction, double slit diffraction, and this N slit diffraction, which is also known as a plane transmission grating, or you can say diffraction grating. So we have seen there that how you are getting principal maximas in single slit, minimas, what are the conditions under which you can get minima there, your secondary maxima. So we have seen the different conditions there. We have seen the entire diffraction pattern for single slit as well as for double slit, and what we have concluded that when we are going from single slit to double slit, then the intensity of principal maxima, when we are going from single to double slit, the intensity of principal maxima is 4 times the intensity of principal maxima of single slit. And when we are going from single to N slit, then what we have observed that the intensity of the principal maxima in case of N slit is basically directly depends upon the square of number of slits. Means the greater of number of slits, the greater will be the intensity of principal maximas. So that we have seen in case of single, double and N slit. After that we have discussed that how many orders can be visible through a diffraction grating. So we have seen this under the topic that maximum possible order observed with the help of a grating. Then we have also found an expression for the missing order spectra, that if you are getting a diffraction pattern, you are getting different orders in that particular diffraction pattern, then there can be certain orders which can be missing from that diffraction pattern. So what is the condition and through which you can decide that which order can be missing from a spectra. So as you have seen there that the missing order is purely depending upon the dimension of that particular slit, the slit which you are using, and the relationship of that dimension of the slit, which is known as grating element, with the wavelength of light source. So that is going to decide the missing order, the maximum possible order. After that we have discussed about the dispersive power of a grating, means the rate of change of angle of diffraction with the change in wavelength. That is actually the dispersive power of a grating, that how the angle of diffraction changes with the change in wavelength. Now the last topic which I am going to take here today, that is resolving power and Rayleigh criteria of resolution, and using this we will find the resolving power of a grating. So these are the topics for today's discussion here. So in my last lecture I have mentioned about that what is the resolving power, what is the meaning of this term. So as I mentioned there, the resolving power of an instrument is the ability of that instrument to distinguish two closely spaced objects. So that is known as resolving power of an optical instrument. For example, if you are using a telescope, as you know, the telescope that is used to see the distant objects. Now those distant objects, they cannot be seen through naked eyes. Suppose you want to observe two stars, then through naked eyes it is not possible to get a clear view of those distant objects. So we can use a telescope. So the ability of that telescope to distinguish between those two stars, that is known as its resolving power. And this resolving power is related with this limit of resolution. So this limit of resolution is basically defined as the smallest angle subtended at its objective by two point objects, and this resolving power is inversely proportional to this resolution limit or limit of resolution. Means the greater the this limit of resolution, then smaller will be the resolving power. It means that limit of resolution should be very, very small, only then the resolving power will be higher. So now I am going to take today's topic here, that is our Rayleigh criteria of resolution. So in order to understand this Rayleigh criteria of resolution, we are taking a simple example of two different sources. So you are having two sources, and those two sources, the difference in their wavelength is very, very small. So suppose you have a light source with wavelength lambda, and the other one, the second source, that is having wavelength lambda plus d lambda. It means the difference between the wavelength, this second source is having a wavelength lambda plus d lambda. The difference between the wavelength of those two sources is very small, that is d lambda, and d lambda is very, very small. Now we want to resolve between the diffraction patterns which are observed through those two sources. So now we are having this Rayleigh criteria. If the Rayleigh criteria will be fulfilled, then we can differentiate between those two sources. So let's try to understand what is the meaning of this Rayleigh criteria. The 2 point sources or two spectral lines of equal intensity or slightly different intensities, or there is a very small difference in their intensities, are just resolved by an optical instrument when the central maxima of the diffraction pattern due to one of the source, you are having two sources and the intensity of those two sources is either that intensity is equal to each other, or there is a very small difference in their intensities. So you can resolve between the diffraction pattern of these two if the central maxima of the diffraction pattern due to one of the source that falls on first minima of the diffraction pattern of the other source. I hope you are getting this point. What I am saying, you are having two sources and there is a very small difference in their wavelength. If lambda is the wavelength of one of the source and lambda plus d lambda is the wavelength of the other source, and that d lambda, the difference between the wavelength of these two sources is very, very small. The intensity of these two sources that is very close to each other, either that is equal or close to each other. Now, according to Rayleigh criteria, we can resolve between the diffraction patterns of these two if the principal maxima, or you can say if the central maxima of the diffraction pattern due to one of the source, suppose we are saying we are having central maxima of the source of wavelength lambda. If that central maxima is observed at theta angle of diffraction and the first minima of the second source, means the source of wavelength lambda plus d lambda, if that first minima of the second source is also observed at same angle of diffraction, then those two sources, those two diffraction patterns can be resolved. That is the criteria of resolving between the two diffraction patterns. So this is known as the Rayleigh criteria of resolution. So let's try to understand this Rayleigh criteria of resolution with the help of this simple diagram. So as you can see here, these are the diffraction patterns of two stars which are which we have to resolve with the help of an optical instrument. So the criteria is, in the first case, you can see here, this is your case number C or third case. In this particular case, the two diffraction patterns, they will get overlap. These maximas, one of the maxima is because of the first source and the other maxima is because of the second source of wavelength lambda plus d lambda. These two sources, since their intensity is very close to each other, the diffraction patterns of these two will overlap and these two will appear as a single diffraction pattern. Means these peaks are going to overlap and they will appear like that these two are coming from a same source. So you cannot resolve between these two. You cannot make you cannot make out that there are two stars because of which you are getting this type of a pattern here. So when these two will overlap, when they are not resolvable, then these two peaks or the spectrum due to these two sources will overlap and they will appear like they are coming from a single source, from a single star. So this is the case when the stars are not resolvable. Now the second one, this is the second case. As you can see, in this particular case, the maxima due to one of the source, suppose I am saying this is for lambda and this is for lambda plus d lambda. If the central maxima of the first source, if it is observed at theta angle and the minima of the second source, that is lambda plus d lambda, if the minima of the second source that is also observed at same angle theta, means the central maxima of the first one that is coinciding with the minima, first minima of the second source, then at that point, instead of a single peak, initially both the peaks or both the patterns were overlapping and they were appearing like that they are coming from a single source. But now if this condition, which is known as your Rayleigh criteria, if this Rayleigh criteria will be fulfilled, then instead of those two peaks, you are going to get a dip in the diffraction pattern, and that dip is going to indicate, now you are going to get a dip here, and that dip is going to indicate the presence of two different diffraction patterns. You can see like this. Initially these two are overlapping, they are appearing to come from a single source. So it is appearing like that you are getting a pattern due to single star. But if the Rayleigh criteria will be fulfilled, means if the maxima, central maxima of the one source is coinciding with the first minima of the other source, then you are going to get this type of dip in the diffraction pattern, and this dip is indicating that instead of a single source, there are two different sources from where you are getting these peaks, from where you are getting this type of diffraction pattern. So you can see here, these two stars are just resolvable. This particular point where this Rayleigh criteria is fulfilled, that is known as point of just resolution, right? And after the point of just resolution, these two images or these two sources or these two stars, they can be clearly seen through the optical instrument. Means now you can easily make out that you are having two stars, you are having two different diffraction patterns coming from two different sources, from two different stars. So now these two stars are clearly resolvable as their airy discs do not overlap, whereas you can see there is overlapping of these two, and when there is overlap, it means those two are appearing like they are coming from a single source. So you cannot decide here that whether the diffraction, whether the pattern is because of a single star or because of the two different stars. So if the Rayleigh criteria, once the Rayleigh criteria is fulfilled, so that is a point where you can just resolve those two diffraction patterns. So as you can see here, these two stars are just resolvable. Although the airy disk overlap, they are separated by more than the airy disk radius. So basically you are going to get a dip there, and that dip is indicating that there are two different stars, and because of those two different stars you are getting those two different patterns. So after that, once that criteria is fulfilled, once that Rayleigh criteria is fulfilled, you can get two different disks here, you can get two different, you can decide that there are two different stars, and because of those two different stars you are getting those two diffraction patterns. So that is the Rayleigh criteria of resolution, which must be fulfilled. If that is fulfilled, only then you can differentiate between the two different diffraction patterns. So when d lambda is sufficiently large, then the central maxima due to two wavelengths are quite separated, as you can see in figure number 1. If the difference in the wavelength of lambda and lambda plus d lambda is large, if that difference is large, you can easily decide that there are two different diffraction patterns, right? If the central maxima of one of the source that coincides with the first minima of other, as shown in case number 2, then the two spectral lines are just resolved. So you can see here, when the central maxima of one of the source that is overlapping with the first minima of the other one, then you can see, then you can say that these are resolvable now. And the third, but when d lambda is very small, then the limiting value satisfying the condition of Rayleigh criteria, then the two different diffraction patterns overlap, as in this figure number 3. As you can see here, when d lambda is very small, then these two, they will overlap, and when they will overlap, these two will appear that they are coming from two different sources. Clear? So there is a limit of every optical instrument. Up to that particular limit you can resolve through that instrument. So now we have to find that resolving power of plane transmission grating using this Rayleigh criteria of resolution. So resolving power of a grating. So first I am going to define here that what is the meaning of resolving power of a grating. The resolving power of a diffraction grating is the ability to form separate spectral lines for wavelength very close to each other. So again you have a similar type of case. You are having two sources, one is of wavelength lambda and the other one is of wavelength lambda plus d lambda. Now the ability of this instrument to separate spectral lines for wavelengths which are very close to each other, that is known as its resolving power. And basically this resolving power of this plane transmission grating, if it is going to resolve these two, that one is of wavelength lambda and the other one is of wavelength lambda plus d lambda, then the resolving power is actually for this grating is defined as wavelength of one of the source to the difference in the wavelength of the two sources. So this lambda by d lambda, this is known as resolving power of a grating. Now how you will get the value of this lambda by d lambda, that we will get with the help of this Rayleigh criteria of resolution. So in order to find this resolving power, what we are going to do here, a parallel beam of light of wavelengths lambda and lambda plus d lambda. So here you have two different wavelengths or two different sources, one is of wavelength lambda and the other one is wavelength lambda plus d lambda, is incident normally on a plane transmission grating having grating element E plus D, and total number of lines on that grating is n. Means you have a plane transmission grating, it is like a glass plate, and over that glass plate you are having a layer, and then with the help of diamond pen the lines are drawn over that grating. So let n is the number of lines or number of rulings on that grating. Now if the nth order principal maxima of wavelength lambda is observed at this angle theta, you know what is the condition for nth maxima in a plane transmission grating. You know that famous grating equation. This is your grating equation, E plus D sine theta is equal to n lambda. You can see here, this one is your grating element, theta is the angle of diffraction, and n is the order of maxima. So if for the first source, that source is having wavelength lambda, if its nth order maxima is observed at theta, then you are having this equation number 1. So this is your grating, this is arrangement of n slits. Now it is illuminated with the help of a light source of wavelength lambda, and you will get the diffraction pattern over the screen. Then this this grating is again illuminated with the help of second source, that is lambda plus d lambda. So now we have to resolve between the two different diffraction patterns. So you know you can resolve between the two diffraction patterns if the nth order maxima if the nth order maxima of this particular source is coinciding with the minima next to nth order maxima of the second source, only then you are going to resolve between the two diffraction patterns. So how we are going to resolve it? So that we will find with the help of again using the condition of maximas and minimas. Then the first minima adjacent to nth maxima, let it is observed at theta plus d theta. So your nth order maxima that was observed at theta, and next to this nth order maxima we are having a minima, and that minima is observed at theta plus d theta. So you know the condition of minima is this, that is n into e plus d sin theta plus d theta is equal to m lambda, where m represent the minima here, m is the order of minima here. Now if the nth maxima of the second source, so what is your second source? Your second source is of wavelength lambda plus d lambda. If the nth maxima of that second source is observed at theta plus d theta, then the Rayleigh criteria will be fulfilled. I hope you are getting this point. What I am saying, nth order maxima of the first source that is observed at theta, and minima next to this that is observed at theta plus d theta. Now for the second source, if nth order maxima, if it is observed at same angle, that is theta plus d theta, then the nth order maxima of one of the source is coinciding with the minima of the other source, then Rayleigh criteria is fulfilled. Then you can find the resolving power of that grating. You can resolve between the two different diffraction patterns. So what I am going to do here, you are having this n into e plus d sin theta plus d theta equals to m lambda. First I am going to decide what will be the value of m. You know, in case of minima, this m can take all the possible values except 0, n, 2n, 3n up to n into n. It means this for nth order minima, for nth order maxima, this order will be n into n. Means the minima next to that nth order maxima, that order of that minima can be n into n plus 1, or you can take n into n minus 1. So when I will take this angle as theta plus d theta, I am taking this order as n into n plus 1. And if I will take angle of diffraction as theta minus d theta, then I will take the order of minima as n into n minus 1. So that's the way I have decided the order of minima here. So you are getting this equation number 3 here. This is your equation number 3. Now what I have told you, that in order to satisfy the Rayleigh criteria for the second source, that is source of wavelength lambda plus d lambda, its nth order maxima is also observed at theta plus d theta, then the Rayleigh criteria will be fulfilled. So if you are getting nth order maxima at theta plus d theta for the second source, then the grating equation that will give you this nth order maxima for the second source. So you are getting equation number 4 here. If I will multiply this equation with capital N, you are getting n into e plus d sin theta plus d theta equals to n lambda plus d lambda. Just simplify it, you will get n lambda plus n d lambda, right? And you know this left hand side of equation number 5, that is already known from this equation number 3. So you can substitute your equation number 3 in equation number 5. So from 3 and 5, what is the conclusion here? You are getting lambda equals to n into capital N d lambda. So this ratio of lambda and d lambda, which is actually the resolving power of the grating, that is equal to n into capital N. So what is small n and capital N here? This small n actually it represents the order of maxima here, and the capital N that represent the number of lines over the plane transmission grating or over that diffraction grating. So you can easily see here that if the grating is fixed, then number of lines are fixed, then this resolving power that depends upon the order, means higher the order, higher will be the resolving power of the grating. So this resolving power for a fixed grating, it directly depends upon the order of maxima. And if I am saying order is fixed, if I'm taking only first order, then this small n is fixed. In that case, the resolving power that depends upon the specification of the grating, means greater the number of lines on grating, greater will be the resolving power of that grating or diffraction grating or plane transmission grating. So this is the resolving power of this diffraction grating, which can be calculated using Rayleigh criteria of resolution, right? So that was the last topic of diffraction. So let's solve few numericals based upon this diffraction. So I am taking this question here. Find the maximum number of spectrum visible in a diffraction grating for normal incidence of light wavelength or light of wavelength 600 nanometer and grating has 3000 lines per inch. So let's try to understand what is the meaning of this question. So you have a grating here, and over this grating there are 3000 lines in 1 inch. Suppose this particular grating is of 1 inch. So according to the question, in this 1 inch, in this particular portion, you are having 3000 lines. So if there are 3000 lines, then you will get this E 3000 times here, because you will draw 3000 lines here. So the spacing between two lines, that is your E, and the width of the line, that is your D. It means you are getting this E 3000 times in 1 inch, and you are getting this D 3000 times in this slit. So it means 3000 times E plus 3000 times D, that will be your 1 inch, and you know the portion of 1 inch in centimeter, it will be 2.54 centimeter. So we have this grating element from this simple expression, and that grating element is 2.54 upon 3000. This is our grating element, right? So what we have to calculate? We have to calculate the maximum possible order. So in order to calculate it, you have this grating equation, and from the grating equation you can see that n will be maximum if this sin theta will take its maximum value, and the maximum value of sin theta is 1. So the maximum possible order is E plus D by lambda. You know the value of E plus D, which we have already calculated for this grating, which is 2.54 upon 3000. So you have to substitute that. So you have 2.54 upon 3000, and we have converted it into meters. So we have multiplied it with the 10 raised to power minus 2 here, and after substituting the value of wavelength here, which is 6000 angstrom here, that is given. The wavelength of light is 6000 angstrom. So you have to substitute it, and after substitution, this is 600 nanometer actually. So 600 nanometer means 600 into 10 raised to power minus 9 meter. So after substitution, you are getting this n max, that is 14, means the maximum possible order which we can get through this grating, whose specification is that there are 3000 lines in 1 inch, and the wavelength of the light source is 600 nanometer. So this is the way through which you can calculate the maximum possible order for a grating. So depending upon the maximum possible order, the missing order, you can solve different numericals. Like suppose you have a grating in which the grating element, that is E plus D, if this grating element that lies between lambda and 5 lambda, suppose it is ranging from lambda to 5 lambda, and you have to calculate the maximum possible order. You know the maximum possible order is given by E plus D by lambda. So you can see the maximum value is less than 5 lambda here. It means the maximum possible order will be less than 5. So less than 5 means 4. So in that case, you will say the maximum possible order for this particular grating is 4. So this is the way you can solve numericals based upon this plane transmission grating or diffraction grating. So that's all for these were the topics related to diffraction. So go through single slit diffraction, go through all the conditions of principal maximas, minima, secondary maximas, then double slit diffraction, then n slit diffraction. Just try to identify the similarities and differences between single, double and n slit, so you can easily understand the concept. So that's all for today. Thank you so much.